Standard reinforcement learning dictates the use of linear reward composition. The idea is to define some weights assigning the importance of each objective, running an RL algorithm, observing the learned behavior, and then iteratively modifying the weights accordingly. However, this process is severely flawed, as it often leads to reward hacking. We show such a case in the Hopper v4 environment, where vastly different behaviors yield similar rewards. On the left, a hopper merely stands in place, accumulating staying alive rewards without progress. On the right, the agent makes significant progress towards our intended task objective but dies earlier. We term the gap between this expected behavior and what the optimization process produces as the intent-to-behavior gap. By carefully designing specification around how fulfilled objectives are during optimization, we show that we can more accurately represent our intentions as optimizable functions. We rely on the power mean as the bedrock for our specifications. Depending on the value of p, the power mean becomes the minimum, maximum, harmonic, geometric, arithmetic mean, or root mean square. By choosing p to be smaller, the composition is pessimistic, focusing on the least fulfilled objectives. With higher powers of p, it is optimistic instead, focusing on the most fulfilled objectives, thus serving as our operator for building fulfillment priority logic, which describes how we prioritize the fulfillment level of various objectives, as described in our semantics. We can perform ands, ors, nots, and priority offsets. Now imagine having speed and power efficiency as objectives, each represented as a fulfillment variable between 0 and 1. We want to fulfill both objectives or reach a compromise, capturing the semantics of an and, high speed and good power efficiency. Here, an objective with low fulfillment becomes more important than one with high fulfillment. The value of p determines how strongly we favor this trade-off. Here we'll showcase what happens when objectives compete, described by two noisy fulfillment variables. f1 in orange is always initialized higher than f0 in blue. We perform stochastic gradient descent on their power mean and present their evolution. As p increases, you'll notice that we slowly go from compromising behavior to exploitative behavior, whereby f1 gets fully fulfilled at the cost of f0. It is especially illuminating to see that when p is equal to 1, representing linear utilities, that it behaves more like an OR in this system. We use fulfillment priority logic to define the specification of lunar lander, showing the difference in behavior between our algorithm, balanced policy gradient, and soft actor critic. For lander, we build a Markovian curriculum, firstly prioritizing getting close to the target, then landing, then minimizing fuel consumption. This translates in our specification as priorities that are offset by 0.1 and 0.5, then AND together. Notice that in the beginning of training, on the top left, our method gets lander towards the target, then it starts to land, then in the end on the right, it minimizes fuel consumption following our logic. Although soft actor critic solves the environment, albeit with significant fuel consumption, we can see that similar behavior emerges after 5 times more training steps than under our method.